watch some part of the lecture a little bit later on, catch up on something that you missed or you weren't really sure about, you will be more than welcome to. So with that, let's take a jump on over to our Google Classroom, which is this one. All right, so here we are at the tail end of week 3. One thing that I wanted to mention, only a couple of people have turned in that handwritten assignment that I talked about on Tuesday that got assigned on Wednesday about writing about charges and how they're made and what happens when like and unlike charges come together. So please do get that written up and turned in as soon as possible. Like I was saying on Tuesday, at the end of this term and at the beginning of the next term, the Excel Center is doing a whole writing campaign to try and collect students' writing and use it to kind of see how people are developing in their writing skills as their time at the center goes on. So if you didn't get it turned in yesterday, not a huge deal, but please do your best to get it turned in by sometime later this week or next week. I will go ahead and let you know we're going to be doing a couple more of those by the time that we reach the end of the class. So next week, I think that there's going to be 2 handwritten assignments that get posted. So the sooner that you can finish up Wednesday's assignment, the less you'll have to worry about, and you'll be able to jump straight into the ones for next week. All right, so that's not the right one. Here we go. So today's notes, like I was saying, has to do with electric current. So on Tuesday, we were talking about electric charges and how we get those positive and negative charges going on by moving those electrons from place to place. Today, we're going to talk about how electricity continuously flows through this cycle. So instead of just moving and being all done, a current is when things flow constantly. So we are going to talk about what causes the electricity to flow, how scientists measure exactly how much electricity is flowing and how much push there is behind that electricity. We're going to get into resistance, or what are things that slow down how quickly electricity can move. And at the very end, we're going to talk a little bit about circuits and the kind of basic ways to draw out a circuit. So electric current is what we're going to be focusing on today. As always, I'll try to stop periodically to ask about if anybody has any questions or is confused about anything. But if you do have a question as I'm going through, or you need me to slow down a little bit or go over something again, please feel free to interrupt and ask me to go over a slide again. So electric current, how do we get that electricity to move around? So static electricity and current electricity are kind of 2 sides of the same coin. Yesterday, we were mostly talking about static electricity. So static electricity is just a fancy science way of saying electricity that is stationary. So static in science means like not moving, staying still. So that's like when we talked about the friction buildup of charge where you rub the balloon against your head and you get the electrons to move from one area to the other. Once you pull that away, everything stops moving, right? Now your balloon with all your electrons on it has a negative charge, but that negative charge is just kind of sitting on the surface of the balloon. It's not like zooming all around the balloon. It's just kind of sitting there. So that's what we were going over yesterday with static electricity. Current electricity is when those electrical charges are flowing very rapidly. Yes, Gerson, this is exactly where AC and DC come into play. So the C in AC and DC stands for current. So those are 2 different types of current. We're not really going to get into them today because they can be a little bit confusing. Essentially, the main difference is that AC is alternating current, which is where the electricity travels back and forth very quickly over the conductor. DC is direct current, which is where electricity is only traveling in one direction throughout the whole current, the whole system. So the AC and DC current, we have electric charges that are moving very quickly through some sort of conductor. So at the end of the day on Tuesday, we talked about conductors. They're things like metals, and they're very, very good at moving electrons and electricity from place to place. So the main way that we get electricity to move is that we have to have something that's kind of moving it or pushing it along. And so you'll see a lot of the examples that I go over today. We're going to be comparing electricity flow to water flow because they act kind of similarly. In water, we can get water to flow from an area of high pressure, so where maybe there's a lot of water over here, or it's like up somewhere high on a hill, to areas of low pressure, further down the hill that the water can flow down. In electric current, we have something similar, except it has to do with voltage. So we'll talk about voltage a lot more in a couple slides, but voltage is essentially the thing that pushes those electric charges along. So in water, we have some sort of pressure difference or some sort of height difference that's causing the water to move. In electric current, we have a voltage difference. We're pushing that electricity from a high voltage area to a low voltage area. And we'll talk about exactly how that works in a couple of slides. So static electricity is when the charges just sit there and don't really move. Current electricity is when the electricity is flowing like water. It's traveling through some sort of wire or metal sheet or some other conductor. So we talked a lot about the different types of positive and negative charges with our static electricity on Tuesday. Does anybody remember which charges are the ones that move? We have our positive protons and our negative electrons, which are the ones that move from material to material or from place to place.
The electrons?
The electrons. Bingo. Ooh, not quite, Gerson. Remember, the protons are hanging out in the middle of those atoms. So we talked a lot on Tuesday about how we have the atoms, which have like the protons and neutrons that are clumped together in the middle, and the electrons that are kind of circling around the outside. So it's the electrons that are the ones that are moving. So we have all these little negative charges that are moving along, and that is what's creating our electric current. Are these electrons moving along some sort of conductor, usually some sort of wire or wiring. So that's what all the little minus signs in this picture down here represent. These are our little electrons that are moving from place to place. So, like I was saying earlier, a good way to think about how electricity moves is to think about how water moves. So we have these tubes for water to move through. Those are like our wires in electricity. We have the water itself, which is like our electric charges that are flowing through our system. We usually have something that our water is flowing through, either a turbine, if it's like an electric generator, or coming out of your sink or something like that and down into your drain. And electricity, we pass through things like light bulbs and circuits and stuff like that. And then finally, we have something that pushes our current along. In a water system, we have some sort of pump, right? This is what circulates the water and pushes it through our tubes. If this was just one long pipe, the water would just sit there, right? It's not going to move all on its own. It needs something to push it. Same thing with electricity. So in electricity, instead of using a pump, we use a battery. So a battery is like our electrical pump. It pushes electrons along away from the minus end of the battery and towards the positive end of the battery. So if you ever looked at like a Duracell, right, it's got like the flat part on the bottom and the little bump on the top. The flat part is the minus side and the bump part is the positive side. And so our battery essentially pushes our electrons through our wire and through, in this case, a light bulb in order to light it up. So the battery is providing the push. Same thing with our water pump over here. Another thing to note is that our water can only pump if it is in a closed loop, meaning that if there's like a leak somewhere, then the water is going to get pushed out of the side, right? It's not going to make it all the way up here. It's going to be lost. Similar idea with our electricity. The charge can only flow if the wire makes a complete loop. Right, exactly, Gerson. We have to make a complete circuit in order to get electricity to flow. If the wire is broken or you take out the battery, then all the charges are just going to stop in place. They're going to stop moving because their loop got broken. So if you took like some scissors and cut the wire right here, the light bulb's going to turn off because the electrons can't flow through that circuit anymore. So they all stop because they're not able to keep going. So again, just like if you're on a hill or something, or you have like a water slide, the water naturally flows from the higher elevation to the lower elevation due to gravity. Same thing with using a battery to power our system. The negative side of the battery is the higher voltage side. The positive side of the battery is the lower voltage side. And so it naturally pushes electric charges from the high side to the low side. And that's how we're able to complete that circuit and get those electrons looping around. So how do scientists actually measure how much current is in our system? How much current is in our wire? So the way we measure it is looking at how much charge passes through a point or a spot on the wire at a particular time. So our super basic equation looks like this. We have our amount of charge on the top and the time on the bottom. So if you do charge divided by time, you get the current. How much charge passes through a point on the wire over a certain amount of time. In extra sciencey terms, we represent current with an I. Don't ask me why. C was already taken by something else in physics, and so they decided I works. Charge is Q. Again, got too many C words, need to use something else. And then time, luckily, gets to stay as T. So current equals charge divided by time, or I equals Q divided by T. So the measurement of current, like the amount of current that we have, is 1 coulomb of charge. So remember, a coulomb is the amount of like 6.25. How much is 10 to the 18th? It's like billions of electrons, right? So if we have remember, electrons are super incredibly itty bitty tiny. So if we have 6.25 billion electrons going through a certain point every second, we have 1 ampere, also known as amp. So if you ever hear about the amount of amps that are passing through a system, that's talking about the current. So 1 amp is equal to 1 coulomb per second. If you have 3 coulombs going through every second, you would have 3 amps of current in your circuit. So with that, I was just going to do some quick kind of basic examples with you guys to kind of show you how the different ways that we can measure current. So, like I said, if we have 1 coulomb of charge and 1 second, remember our current is equal to charge divided by time. So that is 1 amp. Amp is also sometimes just written as A. What about if we have something that measures in 5-second periods? So we get 10 coulombs of charge in 2 seconds. So if this is what we measure, 10 coulombs in 2 seconds.
So would it be double?
Not quite, because the amount of time doubled, but the amount of charge went up by a whole lot. So if 10 coulombs go by in 2 seconds, how many amps do we have running through our system? Remember, our current is our charge divided by our time. Coulombs over seconds. So how many?
So 5.
Yeah, exactly. So if we have 10 coulombs in 5 seconds, that means, or not 5 seconds, sorry. Already getting ahead of myself. 10 coulombs in 2 seconds means that we've got 5 amps of current running through our system.
Makes sense.
All right, cool. So some other things that you can do. Oh, let me check what kind of questions on the thing there are. Hold on here. All right. So with this, we can also move some of these things around in order to figure out some different types of measurements. So, for example, if we know that our is 3 amps, and want to figure out over 10 seconds, how many coulombs are going to flow? So if we have 3 amps of current and we say, okay, if we measure somewhere in 10 seconds, how many coulombs, how much charge are we going to find?
So would we multiply that? Or would we still do the
Hey,
same?
we would. So remember, current equals charge over seconds. So if our current is 3, that's equal to our charge divided by 10 seconds.
So it would be 30 charge?
It would be 30. So yeah, so this would be the same thing as 3 amps times 10 seconds equals some amount of charge. And like you just said, that is equal to 30 coulombs. So if you have 2 of these measurements, you can do some very basic kind of moving around of your numbers in order to figure out the third one. And so the most basic example is when you have charge and time already, you can use our simple little formula to figure out the amps. But if, for example, you know what the amps are and you want to figure out how much charge is going to go through over a certain amount of time, you can move things around. You can also think of it as 1 amp is 1 coulomb per second. So 3 amps is going to be 3 coulombs per second. So that means that if we have 3 coulombs every second, and we're looking at it over 10 seconds, we're going to end up with a total of 30 coulombs. 30 measurements of this charge. All right. Does everybody feel okay with our current
I find this one a lot more easier.
so far? Oh, awesome. That is great. Let's see. Let's do one more example of this. But we'll move things around a little bit more. So let's say if our current is, let's say 7. So we know we have 7 amps of current. And we take a measurement for some unknown time, or we measure over a certain amount of time that, hold on, I'm trying to think of a good number that'll be easy to deal with. Actually, 7 is not good. We'll do 6. 6 is better. All right. So I have 6 amps of current. And over some unknown amount of time, we have 18 coulombs passed by, and we want to know how long does that take to happen. Pull this stuff up a little bit, make it easier to see.
36 seconds.
Not quite, but you're on the right track. So we know our basic equation is, current equals charge over seconds. This is good, charge over time, but we're dealing with coulombs and we're dealing with seconds. And so if we have a current of 6, and we want to know how long it takes 18 to pass by. So in this case, do some super basic algebra, and essentially we just switch the time and the amps. So if we want to know how much time it takes 18 coulombs to pass through in a 6 amp current, we can do our time equals our current divided by our amps. And so 18 coulombs of current, or 18 coulombs of charge in a 6 amp current will pass by in approximately 3 seconds. So again, we have 6 amps is 6 coulombs per second. And so in 1 second, we'll get 6 coulombs. In 2 seconds, we'll get 12 coulombs. And in 3 seconds, we'll get 18 coulombs. So by moving the seconds over here and the amps under the 18.
Is that the formula we'll use for every time we're looking for the seconds?
Yeah, exactly. If you want to figure out, you can do the time equals charge divided by our current. All right, so there are a lot of things like this in physics, where if you know one, or if you know 2 of them, you can figure out what the other one is supposed to be. All right, so most of the homework questions about this are the more straightforward variety, where you have the charge and you have the seconds, and I just want you to figure out how much current that we got going on. All right, so that is the basic measurement of current. How much charge is passing through a certain point on your wire each second. So what this means is that if we have a lot of charges, that could increase our current versus a fewer number of charges. So lots of charge versus small charge, just in terms of like the total amount of electrons that we have in our wire, in our circuit. That could affect how quickly the current flows. But what else could affect it? So what else could give us a large current besides just having more charges. Is there anything that we could be doing to these charges in order to increase our current? I'll give you a little bit of a hint. If these guys...
What was the question? Sorry.
So, yeah, I'll change the question a little bit. If these guys are both flowing at the same speed, then this one is going to have the bigger current because this one has more charges, right? More number of charges. And that's if they're going at the same speed. So what could you do to this current or to these charges in order to get them moving at the same rate as these ones?
Slow down the speed?
All right, you could either slow down this current or you could speed up this current, right? Essentially, if you have a lot of charges, but they're moving very slowly, you might have a small current. Whereas if you have fewer charges, but they're moving very quickly, then you could balance it with the more charges. So it's not just how many actual physical charges you have in there. It also depends on how fast those charges are moving. And that is where voltage comes into play. So the voltage, it's what's created by our battery that we were looking at earlier. So the thing about voltage is that it is part of what is called potential energy. And potential energy just refers to the energy stored in an object. So most times when people think about energy, they think about what's called kinetic energy, which is like the energy of things moving, right? If you see a bullet moving by you really quickly, you know that that bullet has a lot of energy that is pushing it that fast. Potential energy is how much energy is stored up in an object. So an example that I like to think about is think about like a spring, right? When you compress that spring and hold it there, it's not moving, but there's a lot of potential energy, meaning once that spring is released, there's going to be a lot of movement. There's going to be a lot of energy that's released. So if you just squeeze the spring a little bit, you get a little bit of energy back. If you squeeze the spring a lot, you'll get more energy back. The more you compress, squeeze that spring, the greater the potential energy that is stored in the spring. Same thing works with voltage in something like a battery. There's a potential difference in a battery. There is the high voltage negative side. So remember, our electrons are what are moving. So the more electrons there are in an area, the more negative that it is. So our batteries have a negative side and a positive side. The negative side is the high voltage side, and the positive side is the low voltage side. So things naturally want to move from
your camera's on
voltage to the low voltage areas. All right, so this difference in the different sides of the battery is what is pushing those electric charges through your wire, through your circuit. So without that difference, is if everything along your wire is the exact same difference, then nothing is going to move because there's nothing pushing it. So we need this high side, this large voltage and small voltage side of the battery in order to get those electrons moving. So there are whole different types of batteries. We're not really super going to get into them today. there are things like dry or wet cells, which are essentially different types of batteries. So they have some sort of chemical energy in there that gets turned to electrical energy. So like the battery acid that's inside of there is used to create this voltage difference. There's generators, those things where they usually burn some sort of fuel and move a generator in order to turn that mechanical movement energy into electrical energy. And so how big of a difference there is between the positive and negative side of the battery determines how much push or how much force is going to get those electrons to move. And so in physics, we call that the electromotive force, or EMF. So essentially, how much force is there that's going to be pushing on these electrons to get them to move through our system. So one important thing to kind of keep in mind about voltage is that the charges, the electrons themselves, are not coming directly from the battery. Those charges are already in our wire, right? So whatever sort of wiring we're using for this circuit, it's already chock full of electrons. The battery is just what is pushing them, what's getting them to move. It's causing them to move around and around the circuit. So the battery doesn't give electrons to the conductor, to the circuit. The battery just gives that difference in the voltage sides that gives those electrons the push, that basically forces them to move from the high voltage negative side into the low voltage positive side. So our current is how many electrons we have moving past a point over a certain amount of time. It's measured in amps, like we talked about, and it's similar to like how much water. If you think about it in terms of quantities, it's like if you're looking at a stream or a river or a pipe, and you're keeping track of how much water is going through that pipe. Right, so current is just how much of it is moving. Voltage, we measure it in volts. So like you have like a 9-volt battery or a 5-volt battery, or like the voltage and coming out of your wall is like 120 volts, I think. So this would be similar to like the water pressure. So essentially, how hard is the water being pushed out of that pipe or through that river? You could have two different rivers that have the same current, but one is a really wide river that's moving very slowly, whereas the other one is a really small river that's moving very fast. It's like rapids or whitewater. So they both have the same amount of charges that are flowing through a certain area. But in the big river, it's just a lot of charges at one time, versus in the smaller river, it's fewer charges, but they're moving by faster. So the voltage is essentially how quickly are those individual charges moving, whereas the current is how much total charge is moving through your system, through your area. All right, I know it's a little bit tricky. Current and voltage, I always have to go back and remind myself of exactly how they work. But does anybody have any questions about these two properties so far? Anything about current or voltage that you're still a little bit confused about, or you still want a little more explanation on? All right, got it. Thanks, Gerson. So we have a current, how much total charge is moving, And our voltage is what is pushing the charge. It's how quickly are we getting those charges to move. So there's one more thing that we have to think about when it comes to setting up our little circuits, our little flowing charges, and that is resistance. So resistance is something that opposes the flow of electric current. So it's something essentially that slows down the current or makes the current harder to move. A lot of times resistance is provided by things like light bulbs or computer chips or things that the electricity is going through and actually doing some sort of work. So for example, in a light bulb, the way that a light bulb works is inside the glass, there's a little wire, a little filament is what they call it. And as the electricity moves through there, it causes the wire to heat up and start to glow. So there's some resistance between the metal and the wire and the electrons that are going through it. Resistance is what causes the thing to glow. Gerson, you are exactly on the right track. It's not watts. Watts is a little bit different. It's like electrical power, essentially. Ohms, though, is exactly resistance. Annalisa's having some trouble here. Okay. Oh, yes, as the wire, the electricity moves through the wire and encounters resistance. And that resistance causes that filament to heat up and also start to glow. And so your light bulb is lighting up because of that filament in there glowing, and then that's amplified by the fact that usually light bulbs are like a little vacuum. And so that helps it glow even more. Same thing with like if you have an electrical stove, the swirly part on your stove where you actually put your pan down has a lot of resistance to it. And so your stove is trying to push electricity through there really hard. But as that electrical movement is being resisted, it causes heat to be given off from those burners. And so slowing down an electric current, opposing the flow of those electrons, usually causes light and heat to be given off at the point of resistance. So there are different ways that you can alter the resistance of a conductor or some sort of metal. The type of metal that you use is going to have an effect. Some metals are more resistant than other ones. How you set up that metal is going to have an effect. So a big, thick piece of metal is going to have less resistance than a long, skinny piece of metal. All right, it's easier for charges to flow through a big wire than it is through a narrow wire. And the way that we measure resistance, how we actually determine how much electricity is being slowed down, is a unit called the ohm. And so in science, ohm is written out by this fancy omega symbol. Or if you don't want to bother doing that on the computer, you can just write O. But this measures how much electricity essentially is going to be resisted as the current passes through this specific resistor. So we have our three main parts of looking at electric flow. We have current, which is represented by an I, which is just how many electrons are flowing through a conductor in per second, essentially. So we measure that in amps. We have voltage, that potential difference, the thing that is pushing those electrons, which we measure in volts. So the bigger the voltage, the more push you have on your electrons. And we have resistance, which is how easily electricity flows along a certain path. The higher the resistance, the more ohms that you have, the more difficulty electricity has flowing through that material. So this leads us to another kind of basic physics equation, basic physics law. This one is called Ohm's law, named after the same guy who they named the resistance measurement after. So current depends on a balance between voltage and resistance. As you might expect, current and voltage are proportional to each other. They're directly related. The more voltage that you have, the harder you can push those electrons, the more current you're going to get, right? If you have the same amount of electrons and some of them are moving faster than the other ones, those ones are going to have more current. You're going to get more of them through your circuit per second than the slower ones. So the more voltage you got, the harder push you got, and the more current that you have. On the flip side, current is inversely proportional or inversely related to resistance. This makes sense. The more resistance you have, the less current you have. The more your material resists electricity going through it, the slower or the less electricity you're going to be able to get through your system. So current is directly related to voltage, and it's inversely related to resistance. So that means we can create a handy-dandy little current equation. So earlier we were looking at current being the amount of charge per time. We can also measure current by looking at the voltage divided by the resistance. So the amount of push that the electrons are getting from your voltage difference divided by how much resistance they're experiencing as they go through your circuit. So current is equal to voltage divided by resistance. This means that we can also figure out the voltage by doing current times resistance, and we can figure out resistance by doing voltage divided by current. So we have another one of those three measurement equations where if we move them around, if we know two of them, we can figure out the other one. If you remember back when we were doing which one was it? I think it was like the speed and velocity ones. I talked about our little triangle here. So remember, the way that you use the triangle is you cover up the one that you're looking for, and then it tells you what to do with the other two. So for example, if you want to know current, then you cover up current, and it says, okay, if you want to know current, you do V over R, V divided by R, voltage divided by resistance. If you want to know voltage, you cover up the V, and it says, okay, you do I times R. So if they're next to each other, you do times. So V is I times R. And then finally, if you want to know resistance, if you cover up resistance, it says that resistance is equal to V over I, voltage divided by current. So if we do some examples of this, if we know that we have, let's say, 9 volts of voltage, and our resistance is 3 ohms. I'm just going to use O. Actually, I'll do a little O. Write it out. So we want to figure out what is there we go. So from our little equation, we know that current is voltage divided by resistance. So our voltage is 9 and our resistance is 3. What is our total current?
Three.
3, exactly. 3 amps, because remember, current is measured in amps. So if we have 9 volts of voltage powering our system, and it experiences a resistance that measures 3 ohms, then our total current is going to be 3 amps, 3 coulombs of charge per second running through our system. All right, very nice. What about if we know that the current is 7 amps, and our, oops, we have 7 amps of current, and our resistance is, we already used, so let's do 5. We want to figure out our voltage. So if we go back to our little equation over here, we see that voltage,
It'll be the I
I
equals
times
V
R.
over R.
Not quite. So remember, I is our current. We want to know voltage. We want to know V, which is equal to I times R.
Oh, okay.
That's, there we go. So our current is 7. Our resistance is 5. So how many volts do we have powering this system?
35.
35 volts. Bingo. So we have
Okay.
35 volts of potential difference that is pushing 7 amps of current through 5 ohms of resistance. All right, very nice. And then finally, if we know that we have so we know that we have 24 volts hooked up to a system that is pushing 6 amps of current. What sort of resistance do we have in that system? Well, we can go back to our Ohm's law and see that if we want to know what resistance is, that means we have to do volts divided by current. For resistance.
I'm sorry, Mrs. Stanley, you broke up, but you're doing that equation right there, right?
Mhm. Yeah, exactly. So we want to know what resistance is, and Ohm's law says that if we want to know what resistance is, we have to do the equation volts divided by current. So what do we get for our resistance if we do volt divided by current in this example?
Six. What? Hold on.
Load. We got 24 volts divided by how much current do we have?
6, right?
Yep, we got 6 amps of current. What is our total resistance in this circuit?
My bad. It was 4.
4. Perfect. 4 ohms. Exactly.
So when we write out the equation with for the resistance, do we always put 4 ohms? I mean, not 4, but do we put ohms at the end of it?
Mm-hmm. Yeah, resistance is measured in ohms.
Okay.
So I just write it out because I don't want to go through the whole thing and find the symbol on my thing. So yeah, you can either write out for current, we have amps, which is represented by A. For voltage, we have volts, which is represented by V. And for resistance, we have ohms, which you can either write out ohm, or if you're doing it on paper, you can write this little symbol. Or if you're doing it on the computer, you can just write out ohm. Or if you want to be very creative, you can go find it and copy it and put it after your answer. But yeah, is measured in ohms. So yeah, if you ever do a problem where you're looking for current, it'll be measured in amps. If you're looking for voltage, it'll be measured in volts. And if you're looking for resistance, it'll be measured in ohms. All right, very nice. So the very last thing that I wanted to go over with you guys tonight is what exactly are electric circuits. So I've kind of been talking about them in a very general sense about how we have these wires flowing through these batteries. And so in a circuit, we usually have some sort of voltage source, so some sort of battery or generator, some sort of conductor, usually like a little wire, and then some sort of device that is using our electrical energy, whether that is a light bulb or a little motor or whatever it might be. We have some sort of device that is using that energy being provided from our voltage source. So there are a whole bunch of different ways to draw out an electric circuit. We're not really going to get too much into them. Usually, you just use like a simple little line for the wire. So if you want to draw where the electricity is going through your wire, you use just a simple line. And then a battery, normally in an electric circuit, is drawn with one big side and one little side, where the little side is the higher voltage negative side, and the big side is the lower voltage positive side. And remember, the smaller side is pushing the electrons over to the big side. The negative side is pushing to the positive side. Sometimes we have pictures of switches, so things that open and close the circuit, like a light switch, for example, would be represented by like a simple little symbol like this. We have things that measure voltage and amps. And then usually a resistor is represented by a little kind of squiggly line, like this. So like a light bulb or a little motor, something that provides resistance and creates heat or light or motion is a little wavy line resistor. So here we have a basic circuit diagram. Normally when you're drawing circuits, especially if you're hand drawing them, you want your wires to be as straight as possible, right? So that way they don't get confused for something else. It's a lot easier to read if you make it into like a box or a rectangle so that all the different parts are separated out. And there are 4 basic parts to your circuit. You have your voltage provided by some sort of electrical source. You have a switch, something that opens and closes the circuit. You have your load or your resistor, usually like a light bulb or something like that, that provides the resistance. And then you have your wire, which runs through the whole thing. So we have wire, switch, electric source, and resistor. So this makes this is like the most simple circuit diagram that you can make. But it combines all the important parts that you need in order for it to be a full circuit. So in order for electricity to flow and power that resistor, whatever it might be, to turn on that light bulb, you need what's called a closed circuit. So in a closed circuit, the electric pathway is complete. You can run from one end of your voltage all the way through all the different parts to the other. There's no break in your circuit. An open circuit is essentially a dead circuit. It's one where electricity is not flowing because the electric current path is broken somehow. Ideally, it's open because you set it that way, right? When the light in your house is off, that's because your little light switch is an open part of the circuit. So like this guy right here would be an open circuit because all this stuff over here is connected, but our switch is open. So no electricity can flow because this part and this part are not connected. When the switch is closed, when they are connected, when you turn on your light switch, that's when it becomes a closed circuit. That's when the electrons can flow and run through and turn on that light bulb. So closed circuit, everything is working and electricity is flowing. Open circuit, things are not working. The pathway is broken, and so electricity cannot flow. So there are 2 kind of basic types of circuits. One of them is called a series circuit. And a series circuit is basically just a fancy way of saying all of the devices, all of your resistors and batteries are on one single circuit. All right, our electrons are flowing through a wire, they're going through this battery, they're going through this battery, and then they're passing back through or they're going through this light bulb, they're going through this light bulb, and then they're passing back through the battery. So everything is going through one single circuit. What that means, though, is that if any point of this circuit breaks, both of these light bulbs will turn off. They'll no longer function because they're all connected on one series circuit. So this is like if you ever dealt with Christmas lights before and you buy the really, really cheap ones, it's nice because you save some money. The downside is that when one of those bulbs burns out, the whole thing goes off because all of the electricity was passing through each light bulb in series. And so if one of the light bulbs is broken and you have an open circuit, none of the other light bulbs will work because electricity will not flow through there. So obviously this is not great. You'd rather have it to where if one light bulb turns off, all the other ones will still be able to work. In that case, you want something called a parallel circuit. So in a parallel circuit, there are multiple pathways for the current to go through. So as the electrons go through this current, they'll come to this point and they can either go and make this small circuit right here, or they can go and make this big circuit up here. So the current is able to go through multiple pathways. So in this case, if you had a break in the circuit right here, like this wire got cut or this light bulb got burned out, electricity would still flow, your current would still flow, because it could still go through this top circuit up here. Same thing with if one of these wires broke or this light bulb burned out, you'd still have a circuit because the electricity could go through this smaller circuit right here. So these parallel circuits, you're able to have multiple different pathways for the current to go, which means if one pathway breaks down, it won't necessarily affect the other pathways. Now, if one of these wires over here broke, then you'd be in trouble because they are what connect the battery to the rest of the circuit. So you need these ones to work. The other ones, though, like these two right here and these ones up here, if you had one break in there, you'd still be able to have current flow because they would still be connected through the wires and through the battery and through your resistance. So series circuit, everything is on one pathway. So if any point on that path is broken, everything shuts down. Parallel circuit, multiple different pathways, which means if one pathway becomes compromised, it's possible for the other pathways to keep working. All right, anybody have any questions on circuits, some series circuits, parallel circuits, anything?
No, sir, but it's interesting learning about it.
Oh, awesome. I'm glad that you are enjoying it so far. So our current is how much charge that we have flowing through here. It's pushed by our battery, so our voltage is what's giving it the push needed to get those electrons flowing. We have some resistors that are slowing the movement of the electrons, which helps there to be light and heat and other sorts of motion be given off. And it only works if the electricity is able to continuously flow. If you have a break in your system, then that might cause the whole thing to shut down, or it might just cause part of your circuit to shut down. So this is what happens essentially when you turn on a light switch in your house. You're connecting that particular circuit to the flow of electricity that's already going to the other ones. And so the light turns on immediately because the electrons in there start moving as soon as that circuit gets closed. Alrighty, so does anybody have any more questions, anything else about current or voltage or resistance or circuits that you have questions about or they want me to go through again?
No, sir.
All right.
No, Mr. Stanley.
All right, awesome, thanks. So for your homework today that goes along with it, it is some pretty simple questions about determining electric current and voltage and resistance and stuff like that. So it has some sort of definition questions about what exactly is electric current. It has some of those questions that we were going over kind of in the first part of class about how to figure out what your current is if you know how many coulombs that you have going through or how much time those charges spend passing through. You have some questions about defining things like resistance and how resistance is related to the current. And finally, 3 questions about figuring out current if you know resistance and voltage, figuring out voltage if you know your resistance and your current, and figuring out resistance if you know your voltage and your current. So exactly some of the things that we were talking about when we were going over Ohm's law, in addition to some kind of definition questions or basic questions about what exactly is meant by things like current or resistance or voltage. All right, so that is your Thursday assignment. Like you saw, it's only about, what was it, like 10 or 11 questions. Should be pretty straightforward. And then if we look ahead to next week, so at the start of next week on Monday, we have another one of those writing submission questions. Specifically for your Monday assignment, I want you to write about a time when you had problem with an electric current. Either the battery in something was dead, or a light bulb was burned out, or you're having some issues with your Christmas lights, whatever sort of issue with electric current you may have been having. Maybe the breaker in your house wasn't working, something in your house, the electricity got shut off. I want to know essentially what was the problem? How did you solve it? So did you just have to replace the light bulb? Did you have to put in some new batteries? And then specifically, what about your solution helped restore the current? So why did putting in a brand new light bulb make the current flow and electricity turn back on? Why did changing the batteries in your TV remote help to make it so that the current could flow whenever you pushed a button on there? So I want to know about something that you did to help fix an electric current in your house or in your life, and then what it was about that solution that helped you or that actually got the current to start flowing again. So now that you know a little bit about how electric current works, you should be able to determine, all right, when I did that thing, then that was able to restore the flow of electrons because blank. So again, when you do this on Monday, handwritten on your own paper that you can then text or email me a picture of it, make sure you write your full name and date at the top of the paper. The Excel Center is really picky about this, and they won't accept any submissions from teachers that don't have the student's name and date on there. So make sure that you put it on there, or at the very least, keep it around so that if you forgot and I ask you to put it on there, you can just find your paper, write your name and date, and then send me another picture. But that is what you guys got coming up for your final Monday assignment of term 4.
Okay, sounds good.
All right, awesome. Let's go back to the classroom.